How's everyone doing? Having a good Cassandra day? So my name is Evan, and I'm here to talk to you about Spark and Cassandra. So I'm a staff engineer at Ooyala, and been working on Apache, Cassandra, and Spark Cassandra for a number of years. And here to talk about this really interesting fusion of two technologies. So we'll tell you a little bit about how we use Cassandra at Ooyala and how we are integrating Cassandra and Spark, and a little bit about how you can use Spark with Cassandra. So who are we? Just a really brief introduction. Our goal is to power personalized video experiences across all screens. That means in a byteful, let's say that you are watching video on one of our customer sites like ESPN, and whenever you watch a video, we're getting events. We're about a 7-year-old company, and since the very beginning, we've been very focused on analytics. So as of today, we get maybe 2.5 billion analytics pings a day. So that from our customers' customers, and our customers has a pretty big list of some of the top names. Whenever you watch a video on their sites, we are getting data, and we're trying to help them figure out who's watching video and how are they watching it, so that they can improve everyone's experiences with video. We are a fairly large Cassandra user. We have a lot of clusters, ranging from the very small, a few nodes, to over 100 nodes. And it pretty much powers all of our analytics infrastructure, from simple aggregates to more advanced things like machine learning, clustering, trend detection, this kind of thing. And we're running a range of versions from 1.0, or rather the DSE versions of the 1.0 to 1.2. We are hoping to, at some point, we eventually try out the newer versions like 2.0, 2.1. And we are also starting to become a big Spark user. We have multiple teams using Spark, and it seems that, especially recently, Spark has gotten a huge amount of momentum. It is now a top-level Apache project. This quick show of hands, how many people have heard of Spark? So okay, so it's pretty well known. And how many people are actually using it at their companies? Okay, so fairly small. Okay, so I think this is about the right level of talk. We'll go a little bit into what Spark is, and help you guys see the use case for using Spark with Cassandra. So what problem are we trying to solve? And this applies not just to us, but to most people, I imagine, is that we get a lot of data, right? It's not quite that bad, right? But in general, raw data is pretty useless in the sense that you have a lot of it, but you don't quite know how to deal with it. You can't quite present it to your customers, right? So we want to go from mountains of raw data to these nuggets that you can present. And you want to do this quickly and painlessly, as easy as possible, and you want to do it at scale. And no doubt you guys are here because of Apache Cassandra. Cassandra helps with a whole bunch of these things with the quickly and at scale. But let's dive into the problem space a little bit further. So what we have before using Spark is that we have pre-computed aggregates. So for us, our data is defined along several dimensions. For example, geo, such as country, city, device type, things that you get from the user agent, and OS browser, this kind of thing. So what we did was that we would pre-compute, and in Cassandra, this is some of you guys have probably been over at the other talk with data modeling. In Cassandra, it's very popular to denormalize your data. So if we had data that could be sliced 9 different ways, we're just going to compute it 9 different ways and store it. Storage is cheap. And what you get with that is that you get very fast lookups. So for any one of those 9 breakdowns, we can get very fast lookups. We read the data back right away, and everyone's happy, right? The problem with this is that, though, that it's a little bit inflexible, right? So inflexible in terms of the way you query it. Also for us, it was a bit hard to change. So if we needed to do a new kind of query, that meant that you had to add a new column family, and you had to change your entire write pipeline to write things a new way, right? The other problem is that it's hard to know, you need to break down things a lot of different ways. But in fact, most of the data that's written never gets read, because it turns out that people care about certain queries a lot more than others, right? And what happens if we need to do more dynamic queries? For example, one of the dimensions is geo, for example, cities. Another one might be the type of device we were using, such as mobile versus tablet. What if I wanted more complex queries, such as I want to find out the top mobile users in France or something like that. So that involves a cross product. Now, if I had to materialize all the different variations that people could want, this would be that would be really, really hard to do. And you would just run out of space, right? And there might be more interesting kind of queries that you want to query. So the big question is, you want to use Cassandra for scale, but how can you serve more complex queries quickly, right? So you can imagine that there's kind of there's a continuum. On one side of the continuum, let's see, does this actually work? Oh, cool, okay. So on one side of the continuum is, let's say I recompute everything, which is what I was just describing. You get fast lookups, but it's pretty inflexible. On the other hand, you can imagine the totally other end of the spectrum is that my computation is dynamic. In other words, imagine that if I always ran a MapReduce job to get the result I want. So I have a lot of flexibility, but it is really slow. So that's not going to work if you want to answer queries interactively, right? And I think what we really want is we want something in the middle that is partly dynamic and where you can have enough pre-aggregation, but it's also flexible and fast at the same time. So now, why Spark? So a really quick introduction for folks that are not aware. Spark is an in-memory distributed computing framework. It actually does support spilling over results to disk. So it's not strictly in-memory. It's created came out of the UC Berkeley AMP Lab about 3-4 years ago, and initially targeted problems that MR was really bad at, such as iterative algorithms where you need to keep spinning on the same data set again and again, and data mining. It is more general purpose than Hadoop in that it's been applied to all sorts of problems, and right now it is getting a huge amount of momentum. It has just graduated the Apache incubator, so it's now a top-level Apache project. It's getting a lot of contributions, the rate of change in the project is actually accelerating right now. So yeah, a lot of interest. And just a really quick recap of the difference in model between Spark and Hadoop. In Hadoop, we start out with data in HDFS. And what you do is everything's broken down into map reduce phases. So we read data out of HDFS, does some map on it. Then you do a shuffle. And after you reduce the data, then you write it back to HDFS. Now, most jobs don't take more than just one stage. So you end up having multiple stages, which is reading data out, writing it back, reading data out, writing it back, right? So that's how it works. Spark is a little bit different. The first difference is that in Spark, you have higher level operators than just map and reduce. So we have a join operator, for example. And Spark reads the data, transforms it. It might join all this data. This is all happening in memory. And then the magic is that instead of having to write it back to HDFS, you can write it back to HDFS if you want, but you also have the option to cache the intermediate result set in memory. And once this is done, you could then do more transformations, and this is read out of memory at a 10 to 100x speed up compared to Hadoop. And what we find is that throughput and the in-memory is really a huge benefit. So I have 3 use cases here. One is reading out data out of Cassandra when the cache is cold. Another is the throughput I get when I read out of a warm cache. Now, warming your cache does make a huge difference. Although, as most of you know, cache is really hard to control. Like, somebody else would come in and do some other read, and then your cache is kind of thrown out of whack, right? When I cache stuff in Spark, I get about a 10 to 50x speed up, depending on cache and other kinds of things. We find that our developers really like Spark. They're able to get the API really quickly because it's based on high-level data transformations. And it's, compared to Hadoop, the API is much cleaner. And you have an interactive shell. Oops, you have an interactive shell that allows you to experiment very quickly. This is a fun slide. I like showing this. On the right side is the Java MapReduce program for word count. I had to shrink this to about 4-point font to get it to fit on the slide. On the left is it's the same thing done in Spark. It's just 4 lines, basically. So it's pretty amazing. One thing that is cool about Spark is that people have been building components on top. So, for example, one component that's been built on top is called that's just coming out. It's called GraphX. It is a graph computation library, kind of like GraphLab or other things like that. Other things that people have done, Shark is a project for Hive on Spark. You can run your HiveQL, SQL-like queries. And finally, there's something called Spark Streaming, which is basically, you can think of it as like Storm on Spark. You can, basically it does like tiny computations, and people are using this for stream processing, like second latencies, that kind of thing. And what is really neat is that you can build all of this stuff on one platform. So instead of having to manage, there's Hadoop, and then there's Storm, and then there's GraphLab, and then there's like, I don't know, whatever else you use, right? You have one platform that is, you only have to learn to maintain it once. And every time that the base platform improves, it improves the performance of all these different modules. And the other thing that is really cool is that you get really good integration. So it's possible in Spark, for example, to run an SQL or HiveQL query, rather. And you can take the results of that, and you can massage it in Scala Java, feed it into GraphX, or the machine learning library, and then do like modeling on it. So this kind of integration in Spark it's much easier because everything is based on the same kind of platform. And there's also integration with Mesos and Yarn in terms of resource management. I'm not going to spend much time on this, but for those of you guys that use Hive, how many people here use Hive? So a fair bit. Shark is like 100% HiveQL like compatible layer. The reason why it's compatible is because it actually includes a fork of Hive. And so it can reuse Hive, UDFs, SRDs, and that kind of thing. And if you're using DSE, it can actually use, just like DSE has Hive on Cassandra, you can also use Shark on Cassandra using Cassandra as a meta store, which is pretty interesting. So Spark looking pretty good. How do you integrate it with Cassandra? So what we do for a lot of use cases is that we co-locate Cassandra and Spark. So you start with Cassandra at the bottom. we add, this is optional, but you can add some logic for, you can have your own input format or Rdd or that kind of thing. Then we layer Spark on top. Spark talks to init format to read data from Cassandra. Shark, because it's Hive-based, has an additional layer that translates the data into a columnar representation, which is called a Rdd in Hive speak. On top of that, you have a, this looks like single master, but in fact, like Spark actually has multi-master failover based on Zookeeper, as well as if you use Mesos or Yarn, then those things are taken care of for you. And finally, we have a REST job server that serves jobs. So different options for reading from Cassandra. First of all, Spark can take any Hadoop input format. And there's a couple that can read from Cassandra. You guys might all be aware of the base column. There's a column family input format, which is really old. It is basically, it reads all the rows from one column family, which is okay, but not as helpful for most people. There is the CQL paging input format for Cassandra 1.2 and up, which is great. It allows you to use your secondary indexes and gives you a lot more flexibility, gives you automatic paging. You can roll your own. We actually wrote our own input format because we have data that's spread. We had data that's spread across multiple column families, and so we could do joins at read time, as well as we have our own indexes, so we have support for that. In addition, Spark has a native API. I'll go into what an RDD is in a second, but basically I can very easily I can bypass the whole input format and read directly from Spark. I'll go into this in just a second. Finally, there is, as you all know, Cassandra has a native JDBC driver now, and there is someone did write some integration with JDBC, so you could go through that route as well. And I think I left this. Off, but there's also some third-party integrations. There's a company in India called TupoJump that wrote a Cassandra and Spark integration, which looks very slick. Sorry, I'll add this back to my slides at some point. I must have accidentally taken it out. If you're using the column family input format, it translates it directly. Basically, every row in Cassandra gets mapped into one record in Spark. So it's pretty straightforward. And then Spark has operators for operating, and then you can take each row of data and manipulate it in Spark using your join and your other operators. But like I said, it's not a particularly flexible option. I'm going to go into what an RDD is in Spark a little bit, because I just want to make sure you guys are familiar with the terminology. So an RDD stands for a resilient distributed data set. So this is Spark's basic, it's Spark's basic concept, that you have data that is distributed and you can manipulate it like a collection of data. So basically all data sets, RDDs, are divided into partitions. So you can think of a partition as a partition has to live on one node. So if you were to divide your data over 10 nodes, then you would have at least 10 partitions. You could have a lot more than 10 partitions. And yeah, different partitions live on different nodes. In general, you don't have to worry about partitions too much, other than as a sizing kind of thing. In general, in Spark, you're working with individual records. So these partitions would have, I don't know, say, let's say that you have a user database, and so each user is a person. So usually you're working at the user level, you're kind of doing filters on users, but sometimes it is helpful to know the topology underneath. So I just had a quick slide about if you were to choose between reading data using an input format versus and writing using Spark's APIs directly. So I guess the ideal is that one of Cassandra's built-in input formats work for you, like the CQL paging input format. If that works, then that's the easiest route. But if you had to develop an input format versus doing it natively in Spark, I just want to throw up some pointers for comparison. An input format is really flexible because you can use it in Hadoop as well as Spark. On the other hand, I don't know if anyone's tried implementing an input format. It's kind of a big pain. There's like multiple Hadoop APIs, and they're very clunky. It's not the easiest thing to do. So personally, like the lesson that we've learned is that if we had to go back and do it again, we would probably have just gone straight. We would have skipped the input format route and just done it entirely in Spark. It would be much easier to debug and probably saved us about at least a month, maybe more. The only big disadvantage is that you can only use that in Spark. So how would I actually read data from Cassandra like into Spark directly using Spark APIs? So this is how this is in fact how we do some of our reading. You can treat a list of row keys as a distributed data set in Spark. And there's multiple ways of creating that list, but maybe you start up with an index, and your index gives you a set of row keys. So then what you do is that you have a distributed set of row keys. Now I'm going to do something called a flat map. So a flat map takes basically one item, like a row key, and it transforms it into one or more items. And then all those results get become one big data set. So what I'm doing here is that I'm doing let's say you have a function called read columns. Basically, this takes a row key, or in CQL3 it would be like your primary key or whatever, and then you can read in all the data from your row, and then now you have a distributed data set that has all of the data from those rows. The reason why I like to think in terms of row keys is because we know that rows are distributed across a cluster in Cassandra. So if you think of it this way, this maps pretty well to Cassandra's layout because different row keys will go to different nodes. So this is a parallel operation. You can even do, if you want to be very aggressive about this, you can even try to like figure out well which row keys are in which replicas, and therefore try to get a node local read to further optimize this. Although depending on your usage scenario, like for us, most of our Cassandra clusters are in our own data center, so network isn't really isn't really a big factor. So it's not something that we found we really needed to optimize. So our Cassandra Spark architecture. So what we do is that as these events, video events are coming in, let's say they get written to raw logs somewhere. Let's say they're HDFS. So we process the raw logs, and we write semi-aggregated Olap-like tables into Cassandra as a columnar storage. And I'll go into like what kind of schema we use for this. Then what we do is that we load data from Cassandra into memory in Spark, where we can do very fast queries. And we can query it directly using Spark for certain predefined queries. We can query it using Shark for more ad hoc queries. Just wanted to like explain a little bit why it's not enough just to read and write directly from Cassandra. So what we have is that every day we have about over 30 million multi-dimensional fact table rows. And so these are, imagine that you have every combination possible of your different dimensions, your geo and your other things about the user. And there are about 30 million different combinations. Now, for you to answer a query, materializing every possible answer isn't really possible because for us, the user can group by multiple dimensions at the same time. Let's say that you want to group by country as well as browser or something like that, which is not uncommon. Or more common is like, I want to group by video watched and something else, like country. So you end up having a lot of cross-processing. And the number of combinations that are possible from like grouping all these different dimensions as well as filtering and indexing, it's like in the many billions. So it's just not possible to materialize that many answers in Cassandra. So for that reason, we take a different approach. The other approach besides trying to materialize every answer is that you could store your fact tables in Cassandra. This is possible. Let's say that I have 30 million rows in Cassandra, or I could have 30 million columns or something like that. That's possible too. The reason why that doesn't really work either is because depending on the type of query, you're reading from basically for every query you're reading from a random subset of these 30 million rows. So you're talking about a read that is extremely random in nature. I think with SSDs it might be fast enough, but at that scale it becomes, and this is just for one day. When you start going beyond like 30 million, and you're reading random data, it becomes like not, I mean, you can do it, but it will take a long time in Cassandra. And CQL doesn't support some of the higher level constructs like doing aggregations, doing grouping, this kind of thing. Although that's kind of a secondary issue. So our approach is we use Cassandra to store the raw fact tables, and then we optimize the schema for Olap workloads, meaning for very high throughput. And we can read over a subset of tables. And then we use Spark to do the fast in-memory kind of aggregation. So this is what our schema looks like. We have one column family for indexing all of the different Olap tables. We have a metadata family that essentially stores, these are the type of columns that we have and what types of columns they are. Are they integers? Are they whatever? And our main column family that stores data, this basically we store one row per column of data. And the reason why we do that is so that we can selectively load columns. So if someone is running a BigQuery, most of the time they don't need every column. We only load the columns that are needed so that we can minimize I/O. The other thing that we do is why we store things by column is so that you can get very good compression. So you can use a lot of techniques such as dictionary compression, other things. Most columns have a much lower cardinality of values compared to the number of rows that you have. So we're able to achieve very good compression using techniques like that. And we store a whole bunch of rows together that we can read them in big chunks, and it's very fast. Once we have it in memory, what we do is that we pass queries off to our, we have a REST job server. And basically, data is basically stored, loaded from Cassandra into Spark's heap space. And then we run fast query jobs that run off of this memory and return answers to the user. Okay, all right, I guess I could go through this quickly. Just gonna go over really quickly how this works in Spark. Basically, you have records that are distributed across multiple nodes, and in each partition you have multiple records. And then you can convert all these records into a let's say a shark table and run SQL over it, or you can for known queries you can basically use a whole bunch of operators like basic map, sort, group, join, other things like that. There's also a top K operator. So from that point onward, we were relying mostly on Spark to do the distributed data processing. Just a really quick note on fault tolerance. there is, so if this data lives in a heap, you might ask, well, what happens if it goes down? So Spark has a traditional fault tolerance mechanism called lineage. And what lineage says is that I'm going to remember the exact sequence of operations it took to compute this. And so if something fails, what Spark is designed to do is to recompute stuff. In this case, you don't necessarily want to go that route because reading stuff from Cassandra might be slow. So instead, there's different ways. So one way you can take advantage of is that Spark can replicate the memory data set across different nodes. So then that way that survives any one failure. We're also not terribly worried about losing data because in the worst case, we can always read it back from Cassandra, and our schema is optimized for fast throughput. So it's not, so that hasn't been, so having Cassandra there is a pretty big relief, I guess. Cool. I think I don't really have time for a demo. I was just going to show really quickly like how you create tables and read it from Spark. But I think that's probably all the time we have. So thank you very much. Oh, and yes, we are hiring. So.